Hi, I'm Weishi. I'm gonna present a higher order unification algorithm that I have been working on with Dan Friedman, and this is designed for lambda-Kanren. lambda-Kanren was presented at a miniKanren workshop last year. It extends miniKanren with two things. One is higher order unification. The equal operator can recognize alpha, beta, and eta equivalents. The other is lambda-Kanren has a more expressive underlying logic called hereditary hierarchy formulas. Basically, you can put implication and for all quantification in the goal position. And here we're gonna share more findings that we have made recently about the unification algorithm. So in short, with higher order unification, we can have more formulas unified with this equal operator like alpha and beta. And this beta conversion is quite subtle and powerful. So it's not surprising that full higher order unification is undecidable. But fortunately, Miller has identified a fragment of higher order unification, and people call it a pattern unification. So the idea is for the application form, if the head of this application is a unification variable, then all its arguments have to be distinct lambda variables. With such a restriction, and people often call it the pattern restriction, the term of unification looks like this. So basically, the application form is split into two forms. If the head of the application is a unification variable, then all the inputs have to be lambda variables, or here we call names. Otherwise, if it's a lambda variable being its head, then there's no such restriction. So usually people call this variable head a flex term, in a sense that it is flexible. It can be removed by a substitution. If imagine you have a substitution that maps f to some other lambda, then you can remove some variables in this a bar. And if we have a lambda variable as its head, then we call it a rigid application because you cannot remove anything by applying any substitution to it. Okay, so we can run some programs, lambda-Kanren programs, like deciding alpha equivalence. Like here, we have lambda AA versus lambda BB, and they are alpha equivalent. So this query succeeds, and we do not need to instantiate x with anything. So x is just _0. As newcomers to this higher order unification, we might try something more interesting. For example, we can replace the first occurrence of A with a unification variable. Say if we put x here, how can we make it succeed? Well, the answer is you cannot. This is a little bit surprising given the last example succeeds, because intuitively we would think, well, we can associate x with A and it should just work. So that was my first impression too. So, and I was really shocked that it didn't work. So I looked into the unification algorithm, and it looks like this. So this is a variation of Miller's algorithm, and this is like a Nipkow and Prehofer functional version of higher order unification. So these are also rewriting rules of this pattern unification. And you can see we can unify a lambda with another lambda called the binder rule. We can unify two flex variables when they have the same head or they have different head. We can unify a flex versus a rigid. We can versus two rigids when they have the same head. So that's all good. But something is missing. Like if we think about the case just failed, we are missing a rule that is commonly seen in first order unification. which is, well, how about a variable directly unified with another term? This was not in the original rules of higher-order unification. So simply, it cannot handle such a case. And in first-order unification, this case is pretty straightforward, right? Because we can just do a occurrence check to see if f occurs in T. If it does not, then we can extend our substitution, saying, well, f now maps to T. So the first thing we can do is to add a new rule called maybe a var term that unifies a var and a term. And with this rule added, we can run the failed example and expect something different. Well, but it's still the same. And okay, so why is that? And it turns out to be missing this var term is part of the problem, but it's not the root. The root is there's something called the scope restriction. In the sense of higher order unification, we have to think about variable capturing. And variable capturing is handled by these scope restrictions in higher order unification. The idea is all the unification variables are considered existentially bound, and all the lambda variables are considered to be universally bound. So if a unification variable can be instantiated by a lambda variable, then this for all bound variable must occur earlier than this existentially quantified variable. That's quite a mouthful, but in brief, if this lambda A occurs later than this X, then A cannot instantiate X. So why is that? If we think about another example, it may be a little bit clearer. If we think about, we have lambda AX, lambda BB, unify them, and then another pair unifying lambda CX and lambda DD. So in this case, we cannot instantiate X with A, and we cannot instantiate X with C. Neither of them works. So that's the variable capturing problem. For X, A, and C, they are both free variables, and you can just not use free variables in a substitution. So this looks a little bit strange from the perspective of, first order unification, because if you think about our first example, the alpha equivalence, it works, and suddenly then it stops working. And to get away from it, one thing we can do is to treat these lambda variables not as lambda variables, but as constants. So the Brown levels comes to the rescue. If we treat all the lambda variables as the Brown levels, for instance, in this case, lambda AX, we can instantiate X with the Brown number 0. And for the other case, if we instantiate X with 0, then it also works. So we think this is going to generate more intuitive answers, and because it's closer to first order unification. So that's just step number 1, and we cannot use the Brown numbers as a drop-in solution. We will get back to this mystery later, but for now, let's just switch gear a little bit and look at a similar but different problem. That is how alpha equivalence is handled in higher order unification. So if we zoom in into the rules, this rewriting rules, and just focus on the rule of binder-binder. And traditionally, in all literatures on higher order unification, and this binder-binder is handled in this way, and we call it binder merging. So when we are unifying some lambda X S versus lambda YT, we just recursively unify their corresponding subparts S and T with renaming every Y in T to X. So that looks straightforward, and actually it's pretty convenient because now we do not have any alpha equivalence problems. Any alpha equivalence variables will just be, syntactical equivalent. This works for most cases, but not with variable shadowing. So, so that's binary merging. Imagine you have lambda A, lambda B, A apply on B versus lambda C, lambda D, C apply on D. Then binary merging is going to convert the first term to lambda C, lambda D, C versus D. This is fine. Now let's look at an example where name shadowing occurs. So what if we have a name shadowing in the first binary? If we have lambda A X versus lambda C, lambda D, C, then by binary merging, then we will have lambda C dx versus C dc. Then it's kind of obvious that we should instantiate X with C or the round level 0. So in this case, either you are using the round numbers or binary merging, it doesn't really matter. You will end up with a similar result. So here we know X could be 0, but what if we install this 0 back to X and then reify all the names? Then if we go back to the original term, imagine we have lambda AAX, we will have this lambda AAA is equal to lambda CDC. So if our reifier is not carefully designed to recognize such name shadowing problems, we will generate false positives. We may also generate false positives if we are not careful enough, but another direction. So if we have name shadowing in the other term, so in the term that initiates the binary merging, then we have another kind of false positive. Imagine this. The first term will be converted to lambda C, C applied to C. Then these two terms will be unified again. So our solution to solve this problem is to not use binary merging, but use a new way to decide alpha equivalence between names. And we call this static closures. A static closure is just a variable paired with a scope, and the scope is just a list of names. And in addition, we are extending the definition of terms with the Brown levels, because we want to instantiate sometimes instantiate variables with the Brown levels. So this static closure, it should support two operations. One, because it's extend. If you have a static closure phi and you have some new variable a, then extend is going to add this a to phi. And if this a has been previously added, then we are having a name shadowing. So this a should shadow the previous one, and the Brown level of the previous one should be not accessible anymore. And that's about extending, and we can use this static closure. So if we have a scope and a variable, then we can check what is the Brown level. If we have a scope and a Brown level, then we can check whether this the Brown level is actually shadowed. Let's see some examples. So here's the simple case. If we have lambda A, lambda BX versus lambda C, lambda DC, we first convert them to static closures, ABX and the CDC. And for the right-hand side, it's straightforward. So we have a static closure whose term is just a name, and we can convert it to a Brown level. C is not shadowed in this scope, so and it's the Brown level is 0, so it's just 0. And now we have a variable versus the Brown level, and we are trying to instantiate X with 0. Before we can do that, we have to inspect whether level 0 is available in this scope, and fortunately it is. So A is not shadowed, so we can instantiate X with 0. And now if we substitute X with 0 and reify back the names, then we have lambda A, lambda BA versus lambda C, lambda DC. Let's see another example where we have a actual name shadowing. Say if we have lambda A, lambda X versus lambda C, lambda DC. Again, we convert them, both of them, to static closures. We have AAX and the CDC. The right-hand side is the Brown level 0. And now we are trying to instantiate X with 0. Before we can do that, we have to check if 0 is available in its scope. But this time, the first A is shadowed by its successor. So 0 is not available anymore. For the left-hand side, if we apply this scope on 0, we have nothing because it's shadowed. And the right-hand side is just 0, so they do not unify. And so in this case, we can recognize, well, we have a failure. So in short, we're just changing this binary rule, and also for other rules, because we now have this scopes everywhere. So the input of unification now are 2 static closures instead of 2 simple terms. And also for the binary rule, we'll just simply extend the scope. And when we have to compare variable names, we are gonna use the name, the static closure to decide the equivalence of their names.